Hello my friends, welcome again to my video channel. Today we will start a new project. No, not a new repair video, promised. There are two projects in the pipeline regarding repair, but today I will start a project which is the installation of a subtone of this old Braun VHF transceiver. What is a subtone? In the last century, when the first repeater stations were installed in VHF, later in UHF, they got a tone call frequency to open the repeater. When I want to operate over such a repeater, it's necessary, of course, to go FM repeater function. This is a frequency shift of 600 kHz down. And then I have to press the call button for 1 or 2 seconds, only momentarily, not permanent. And when this tone call is received from the repeater opens and is ready for transmission. And then I can transmit over it without tone call, because the call opened the repeater station, and then I can transmit over it. There are different ways to shut down the repeater. Some are shutting down after a certain time, even when a permanent carrier is transmitted, so it's necessary to repeat the call after some, let me say 1-2 minutes, with or without call. I don't know exactly. Some only need an interruption, or others need, as I know, a repetition of the call. Anyhow, this call function was standard for many years in VHF and UHF. This method had a little disadvantage. When there was a second repeater station on the same frequency, let me say 150-200 kilometers away or so, and when I have a good antenna or good conditions, then maybe I will open the second repeater, which I do not want to operate. But it also receives the tone call and also opens. It is not wanted, but it opens. That is part of the system. So there was, I say 20-30 years ago, a better method developed, and this is a subtone. A subtone is part of the coded tone, coded squash system, CTCSS, is a very low frequency, audio frequency. And this audio frequency is transmitted permanently. Not only as a call frequency or a wake up frequency. It is necessary to transmit this frequency permanently. It is not so dangerous because the frequency is rather low. It cannot be heard. And the frequencies start in our region here with 67 Hertz up to, okay, theoretically 250 Hertz. I wouldn't never use it. This is much too high. This can be heard. But frequencies in the range where I live here, I need 71.9, 88.5, 141.3 and 123. I need these for subtones, and the subtones are transmitted permanently. So the repeater sees, okay, there is this frequency on it. It's a coded tone. This is the code, this frequency. Another repeater nearby has another frequency, so he says, no, this is not my frequency, I do not open. So it is necessary to transmit this frequency permanently, and it will not be retransmitted in the output frequency, because the repeater, of course, has a filter for this frequency. He receives it, but it does not retransmit it, so the retransmission is okay. At higher frequencies it will also work, but the problem is when there are some small harmonics of the signal, would be 750 Hertz. For example, third harmonic, this could be heard, but the deviation for this system should be maximum 300 Hertz, not more. And the deviation for a FM signal and the amateur range is 5 kHz. So this deviation is a very small or low deviation, and any harmonics would have a much less deviation. For example, only 10% or so, then they would have 30 or 50 Hertz deviation, and this should not be heard. But the task is now to create such a frequency which can be chosen and to bring it into the transceiver. And this is the first problem now. These low frequencies are not amplified by the microphone amplifier. Microphone amplifiers for FM have the tendency to amplify only higher frequencies in the range of 1 or 2 kilohertz, and lower frequencies below 500 hertz or 300 hertz are suppressed or attenuated. So these frequencies, 71 up down to 67 hertz, cannot be fed directly into the microphone amplifier. So we need a bypass, especially when we swap the frequencies from here to here and here. Then we would need a constant amplification of the microphone amplifier, and it does offshore, of course, not, because this frequency, 71 hertz, will be more attenuated than 141 of one of these frequencies. So we need a direct access to the FM modulator. Here we have the schematic of the FM modulation. In this transceiver we have two oscillators. This is 10.1 MHz for FM repeater operation. This is 10.7 MHz for normal FM simplex operation without repeater function. The difference is 600 kHz. It's a little bit a strange or odd system. This is due to the frequency scheme and the not typical frequency generation of this transceiver. The frequency scheme is a little bit different from others. So I have here two FM modulators and two FM oscillators. We have two cap diodes, one and here and here. Let us explain it with this diode. In FM repeater operation we have here positive supply voltage, which supplies this oscillator here with the crystal. This is a microphone input. This is a plus for the microphone amplifier, and it is amplified. And the collector has two outputs, and this output goes to the cathode of the cap diode. The bias of the diode is set with this trimmer. And here we have the output, F out, from here or from here. The other oscillator has the same principle. Now I need an access to this point for the direct modulation of the cap diode. All other points have a very non-linear frequency characteristic and cannot be used. For example, this input from the microphone amplifier, we have 100 nanofarad in series. You can imagine a frequency of 100 hertz or less is heavily attenuated, and the frequency response between 70, 100 or 150 hertz is not linear. Same problem in the output with this 47 nanofarad. This is also not a constant impedance at various frequencies, only for higher modulation frequencies above 500 hertz. These capacitors have a nearly linear or constant capacitive resistance. I do not swap these capacitors. I do not want to destroy the characteristic. I'm sure the manufacturer knew why he has chosen these values to pronounce higher AF frequencies in the microphone. So my first idea is to add here an external modulation frequency, the so-called subtone frequency, via a resistor. I have to look for the DC potential, not to destroy it. So I can maybe use a big capacitor here in series, but outside, of course, in this chamber there is not enough space for it. I will add a resistor, let me say 100 kilohertz, maybe 200 kilohertz in series, which blocks the AF coming from the microphone amplifier, 6.8 kilo ohm in series. It does not affect it, so it can be fully modulated. And I need, of course, when I have here 100 or 200 kilo ohms, a little bit more amplitude, but that's not the problem. On the other hand, such a high resistor here would have the advantage that any unwanted modulation coming from outside is attenuated. So I have to look for a high series impedance, and I will add a small impedance to ground outside this chamber, and maybe also then a blocking capacitor to block the DC bias. My first test setup will look like this. 100 kilo ohm in series, 1 microfarad in series, and 1 kilo ohm to ground. This 1 microfarad has at 100 Hertz an impedance of 1.59 kilo ohm. That's okay. This in series with 100 kilo ohm, the variation of the XC of the capacitive resistance via the frequency between 70 up to 140 Hertz is not relevant, related to 100 kilo ohm. So I will build up this circuit. This is a feed-through capacitor like here. I will build up this circuit and measure the deviation I get and the needed input voltage. The chassis is out. Meanwhile, I know how to do this. And we have a look at the two FM oscillators, 10.1 MHz and 10.7 MHz. These are the two ports for the BIOS setting. Make it a little bit more clear. Here we have the two ports, and I need access to this cap diode. Where is it? Here it is. This one, and the other one is here. So the best would be to drill a hole on this side and on this side for feed-through capacitors, and then I can wire it on the bottom side of the board directly via this resistor to the diode here and here. And I will add the series capacitor as shown externally, and also the ground connection to prevent any harm, also to make the input rather low ohmic. Next job will be to take out this board, to flip it out. I have to unscrew something and then unscrew the screws, and then I can flip it out and have access to the lower side, and then I hope I can also drill the hole in it. The two FM oscillators are accessible now. I had to remove the shield and 4 screws so I could flip it out. Unfortunately, I have to drill the holes here on this side, not here. A little bit difficult, but I think first we drilled a small hole, a lead, a little bit vertical, not exactly straight horizontal, not possible, this way and this way. And then I will shift up this board so I can drill from the other side the rest. Not very easy. There's some danger to destroy something. I don't want to be a fool for the rest of my life, but I think this will go. First drilling 2 small holes here and here. Now I'll try to drill a hole, the leading hole here and here. It's a question of patience and a calm hand. Through. And through. By the way, these are the feed-through capacitors. The two each have 1 nanofarad. It's okay for the frequency. I will add an additional external capacitor to it. So these capacitors will be used. Now I can increase the drill a little bit and then do the rest from the other side. I could raise the unit, the FM unit, up, and then I can drill this hole bigger. I use for such a work always a hand drill, not a machine. Never use a machine. You know the effect when the drill is nearly through. You are pulled inside and the damage will be nearly infinite. So always do this work by hand, slowly, slowly. Take your time and not to life. The hole is a little bit too low. I have to rise it up, and to make it bigger I use again my small drilling machine and try to and the rest, the fine tuning again, is done with my hand drill. It's 3.5 millimeters. Oops. You have to be careful not to slide too deep inside. Now I'll try whether the feed-through capacitor will slide in. Yes, it fits. Same on the other side. That's it. The two holes are drilled in. One is here, the other one is here. I have to clean all the metal fibers, of course. I cleaned it inside, removed the sharp edges with a drill, and then I can solder in now the feed-through capacitors. The two new feed-through capacitors are soldered in, this one and this one. And now we go to the next step, to the wiring of the resistor and coupling capacitors. This is the first test setup, the first construction. We have here the 1 microfarad capacitor. I could manage to find a small one which fits into the chamber. I think the voltage rating is only 30 or 40 volt, not more, but that's not important here. Here we have the 100K in series, this one, and here this one is the connection to the cathode of the cap diode. Here we have 1K to ground, this resistor in the corner. And here we have the input. Now I will try to use this input as a modulator and see how sensitive it is, how many millivolts we need for a frequency deviation of what I want, 300 Hertz. This is the first test setup, transceiver, deviation meter, connected via this cable and this attenuator to the output. I will reduce the power down to 1 watt or so. And the output of the modulation meter is connected to the scope. And here we have an audio generator, 35 Hertz. I will vary the frequency. In the moment it is not connected, I will only check the standard function again of the transceiver. I go to send and wait until it locks. It has a PLL inside. Seems to be locked. And then I go to call with 1750 Hertz. Approximately 3 kilohertz deviation. Full scale is 5 kilohertz. And here we see the demodulated signal. That's okay. And now we can feed in the signal, the subtone signal, to the connection here. The signal, the AF generator, is connected now to the input. Output voltage is set down to 0. We are on the range of millivolt. Full scale is 30 millivolt. Nearly no modulation. This is only a little bit of noise. I will set it to 0. Noise compensation. It's a rather simple compensation, but it's now centered to 0. The frequency is 35 Hertz. We can use this frequency. And now I will try to get a full scale is 5 kilohertz. We can go to 1.5. Okay, it gets noisy. Full scale is 1.5. So we have here 500 Hertz. When I increase the voltage a little bit, at once we have a signal. Why doesn't it trigger? Too much noise. Okay. I think I have to switch on the noise filter. But we see it's a sine wave. 1 kilohertz deviation. It's much too much. And we need the input voltage of, I go down to 10 millivolt, full scale. That's what we want to have, 300 Hertz approximately. When I go down to 0, we have 0. So we see this is rather sensitive, and we need only an input voltage. When I see it's 10, okay, 3 or 4 millivolt to get a full modulation. So I think I can reduce the resistor from 1 kilo ohm to, let me say, 470 ohm or so. But in general it works. And the most important thing, this deviation has to be independent from the frequency I chose. So I go to higher frequency. Okay, 80 Hertz, but we have less deviation. A little bit suspicious effect. Where is the low pass? When we have a closer look at the schematic, we can see two low pass filters. One low pass filter is 100K and 1 nanofarad to ground, and another low pass filter is generated by this capacitor here. We only have 6.8 kilo ohm in series. This is nearly nothing related to 100K, and this capacitor here is not directly grounded, but it's connected to the plus pole via 10K, and the impedance of the transistor, the output impedance, the emitter is grounded with this capacitor. So the output impedance, collector, emitter, I don't know the value. It's obviously rather high ohmic because it's I think a current source, a voltage driven current source or current drain. But the 10K is also very small, 4.7 nano to ground, okay, another. But this capacitor mainly is also in parallel with this one, and this is a second low pass. So I will calculate 100K 1 nanofarad and 100K times 47 nanofarad. This is a calculation with 1 nanofarad, 1 by 2 pi RC. 2 pi is this one. R is 100 kilo ohm, 100, 10 exponent minus 3. It's shifted up. And 1 nanofarad is 1 exponent 10 exponent 9. Yes, 10 minus 9 here or 10 plus 9 here. So 10 exponent 6. 628, 1.6 kilohertz. This cannot be the problem. But when I use instead of 1 nanofarad, 47 nanofarad, the result is 33.9 hertz. This is more obvious. That's what I've observed, what we could see in the response. So I think the main problem is a 47 nanofarad capacitor. Well, it's a little bit difficult to evaluate it by experiment. I can solder around to find a solution. I will do a simulation with LT-Spice. That's easier, and I will develop a circuit which is in line with this one, what we have, and then I think we can decide how to proceed. Before I start to solder around and swap components, as an idiot, I decided to do an LT-Spice simulation. I will simulate the circuit, input circuit, 1 microfarad or any other capacity, 100K in series. This pot is simulated with a variable resistor to ground. It's not important for the AC response whether we have here DC or not. The AC resistance to ground is decisive because the plus pole is also grounded for AC. This resistor, this capacitor, I also will simulate this transistor circuit with the collector resistor, the positive supply, which comes in here. It's 8.5 volt nominal base and emitter circuit. And this circuit I can simulate now then with a sweep of the incoming of the input frequency. It shows a certain input voltage, and to see how the circuit behaves, and the output at this point where we have the cathode of the cap diode and with the input. Here we have the circuit. This input AC voltage, sweep from 60 Hz to 300 Hz. I will use the steps to 50 Hz. Input circuit, this is 1 microfarad. These are the two components I added to the FM oscillator. Here we have R1. R1 is the trim pot for the DC bias. It has a step of the parameter from 47 to 72 kilo ohm in steps of 5 kilo ohm. This resistor is the series resistance of the 47K and the pot, which we can have as a maximum value. Here we have the transistor circuit, power supply, this is output and this is input. So this circuit is simulated now with the original value of 1 microfarad, and we can start the simulation with the running guy, and this is the output. We can see here the output voltage. These are the parameters of the pot, the various parameters, and here we have the output voltage over the frequency range. And we can see from beginning with 60 or 70 Hz up to 200 Hz, we have an output voltage in the range from 26 millivolt down to 12 millivolt. That's what we observed in the first measurement, that the voltage drops considerably on the cathode of the diode with increasing frequency. This is not a good solution, so we have to select a better one. And by try and error method, reducing this capacity to 10 nanofarad, and then do a new simulation, we suddenly have a rather constant output as we want. And please note this vertical scale is magnified, it's automatically scaled, so the response is rather flat. We are here at 9 millivolt, 9.6 up to 12 millivolt. So this is nearly one horizontal line. When we scale it linearly, top, let's make a tick of 1 millivolt, and we start with 0 millivolt. Then you see that it is nearly constant, maximum and 0 voltage, so we have now a rather linear output, and the variation of the resistor of the BIOS pot is not relevant. It only adds some attenuation or not, but that's not critically, because again we are very linear now over the whole frequency range, and that's what we want. So by try and error I found that 10 nanofarad as coupling capacitor is the best solution. So the final schematic is like this. Instead of 1 microfarad we can use 10 nanofarad. It's a little bit surprising that this small capacitor is good enough for coupling 60-70 Hertz or so, low frequency. But we have here 100 kilo ohm in series. So we have here time constant, and this time constant is obviously the same as the time constant we have here in the rest of the circuit. And this one, it's of course a compromise. It's not a perfect compensation because we have many time constants. One time constant is C1 to ground. We have C2 and R2 in series, but this is C4 to ground. The transistor plays a role, not very important, but it plays a role, and so on. So we always have a compromise, but for the frequency range in discussion, the subtone frequency range, I think with 10 nanofarad we have the best compromise. And now we are at the end of part 1 about the videos about the subtone installation in a Braun SE400. We have seen that we have now a theoretical, simulated solution for the modulation of the FM oscillators to get a linear response. In part 2 we will construct the encoder itself in a small case outside of the SE400. I will use DIN plugs on the rear side of the transceiver to connect it. Stay healthy, stay tuned, see you on this channel.